This is Unit 7, Video 10. In this video we will talk about calorimetry. And the question we'll answer is, how do we measure enthalpy? We talked about enthalpy, delta H, in the previous video. Here we're going to show you how to experimentally measure this to put it at the end of a reaction. We're going to carry out a reaction in an aqueous solution and measure the heat change by measuring the temperature change of the water in the solution. So essentially we're going to run the reaction in a cup, and then we're going to see how much the temperature goes up by, and then from that we will determine the heat change for the reaction. Now here the system, remember the system are the chemicals. We said the chemicals that are reacting is called the system. The system now is dissolved in water, and the surroundings then is everything around it, including the thermometer and also including the water molecules. The water molecules in this case are going to be absorbing that heat from the chemical reaction, and then they will transfer that heat to the thermometer, and the thermometer will take that temperature and find out how much heat was released. And the neat thing about this is you can actually use a small amount of a chemical reaction and then just scale it up to a whole mole for a balanced equation. And that's what we're actually going to do. So you don't have to react a whole mole to get the delta H. You can actually react a small amount and then scale it up. You know, if you have 0.1, if you react at 0.1 grams, then you can say, well, what if I react at 24.3 grams? How much would that be? And the reason you would use a small amount is because you want to minimize error. Number one. Number two, if you want to use water, you'll see that we'll have to use the specific heat of water. And if you use a big amount, that will change the specific heat of water, which will make things more difficult to measure. So using a small amount is actually the way to go. So this is a slight review of the MCAT equation. So the amount of heat released or absorbed will depend on the temperature change, because the higher the temperature, the more heat is needed to raise it. The amount of water, if you have more water, then you can absorb more heat. And then also the heat's capacity of the substance, of the solution. In this case, it's going to be of water. So this is the familiar MCAT equation, except now we're going to say Q equals MCAT. Now Q is actually used in chemistry to represent heat, which is different than delta H. Delta H is usually used for molar amounts. Delta H is usually placed at the end of a reaction. So once you have a reaction, then you can put delta H. So that's how we differentiate between Q and H. Q is before, we'll say, you put it at the end of a reaction, and delta H is after after you're done with it, you can put it at the end of a reaction, if that makes sense. And C is the specific heat. You can also use S for specific heat, but usually we see it as C. Alright, so this equation that we've seen before, that we've worked with, we're going to now apply to chemical reactions. Here we go. A reaction is performed in which 250 grams of water rose from 22 to 98 degrees Celsius. How much heat was released in the reaction? So we're simply applying the MCAT equation. We say Q equals MCAT. Now, in order for this to work mathematically, what you would do, you would actually put a little negative in front of it. So in the previous slide, in fact, on this previous slide, I really should put a negative in front of here in order for it to work mathematically. Let's go ahead and do that. The negative is always placed in front. Let me show you why. So what happens is, in this case, we're going to plug the numbers in, and we'll find out how much heat is released. So the temperature change goes from 22 to 98. The way we calculate that, delta T then, would be calculated as temperature final minus temperature initial. So in our case, the temperature final is 98, the temperature initial is 22. Okay? Which gives us 77 degrees. This is 77 degrees Celsius. Looks like our mass is given to us as 250 grams. So we can go ahead and plug in the value. Well, here, this is 250. The C, remember, is going to be the 4.18 joules per gram degrees Celsius. This is going to be the specific heat of water. Now, we don't have pure water. This is going to be a solution, and the solution's specific heat will actually be the same as that of water. We'll assume that the solution's specific heat is the same as that of water because it's mostly water, and this is actually good approximation. This is true. Okay, so we can just plug the numbers in, In this case, we have 250 grams multiplied by 4.18 joules per gram Celsius, multiplied by our 77 degrees Celsius. And we get here, if we plug this in, let's go ahead and calculate this amount. 250 times 4.18 times 77. We get 80,465. So this is 80,465. This is joules. Since everything else cancels out, remember that the grams cancel out, so does Celsius. We're left with joules, which gives us kilojoules. We convert this to kilojoules, and if we have 3 sig figs, actually we're down to 2 sig figs since we have 77 degrees Celsius, so 80 kilojoules. So this is actually 80 kilojoules. Put a little decimal for 2 sig figs there. 80 kilojoules of heat was released. Now, remember when we said released, that means delta H will be negative. Now this is not delta H, this is still Q. Eventually we will bring this up and scale it up to get the delta H, and that will have to be negative. Well, how do we make sure that we have a negative, that way signs match? What you do is you use this negative in front. In fact, you can say that negative Q equals 8,465. So then what you will do is you transfer this negative over to the other side. Essentially, you're going to divide by -1 to both sides, and that's how you would transfer the negative to this side. So you have negative 80 kilojoules is the heat change, and that's how you can show that heat is released. Now we know it's released because the temperature is going up. If the temp goes up from 22 to 98, the temperature is going up. That means heat was released. The system actually released heat to the thermometer. The thermometer picked up the heat and went up in temperature. So anytime the thermometer goes up in temperature, you'll see that heat is released. And technically, you need to put a negative in front of your number. So we're going to try to keep track of this mathematically properly. All right? So calorimetry is going to be the technique that will be used. We're going to use this MCAT equation in calorimetry. And calorimetry is a fancy word for measuring heat using some sort of device. The simplest device is something called a coffee cup calorimeter, or an insulated cup calorimeter. The temperature change in here essentially is measured. So you need a thermometer. Really, that's all you need. In this case, this is a stirrer. So you can actually stir your reaction. It usually actually has a loop that looks like this, and they use up and down. What you do is you don't swirl it, you go up and down. But you can take the whole thing and just swirl it as well, but that's what's usually done. So the stirrer can help as well, but the most important thing is you're going to be measure the temperature, because you'll know how much is inside of here. You know how much water or how much solution is inside of here. You can measure that. You got your M, you got your delta T, and you'll get your C from the 4.18. You'll assume that the specific heat is the same as that of water. And then we can scale it up and find out the delta H of the reaction. So this is really going to be the method, and we'll do a reaction in a lab or two involving this concept. So really it's temperature. Really all you're doing is you're measuring that temperature of the reaction. Good, so let's go ahead and try this. So we have 2 grams of sodium hydroxide are placed into 100 milliliters of excess HCl solution. We'll say this is solution, this is excess aqueous, AQ. This is aqueous HCl. And the temperature then of the solution goes from 21.0 to 27.5, and we're going to calculate the delta H for the reaction. Specific heat, it says, can be the same as that of water, and the density of the solution we can say is 1 gram per mil. Now usually what you do is you measure the volume of your solution, not the mass. You could measure the mass, but in this case you just measure the volume of the solution. You can put it on the balance, but you can also pour it into a grad cylinder and measure it that way. So what we're saying is that if we have 100 mils, we have 100 grams of the solution because of density. The density is 1.0 grams per mil. All right, our delta H in this case, or rather delta T, sorry. Delta T, we're going from 21 degrees Celsius up to 27.5 degrees Celsius. So our delta T should be 6.5 degrees Celsius is our delta T. Our specific heat looks like is 4.18, so our C is 4.18 joules per gram Celsius. So we can go ahead and apply the MCAT equation. So let's do that here. and we said negative, put little negative to make the signs match up. Negative Q is MCAT. So my mass is 100 grams. My C is 4.18 joules per gram Celsius, and my delta T is 6.5 degrees Celsius. Alright, go ahead and plug this in and see what we get. Let's do 100 times 4.18 times 6.5, and you get yourself 2717. So this is 2717. This would be joules. Let's go ahead and keep some more sig figs just for now. And this will be negative if we transfer the negative over to the other side. This is negative 2717 joules. Okay, we're not finished quite yet. This is Q. This is heat. How much heat was released by the small amount that we reacted. Actually, this is going to be a little different. And this is a good thing that I did this. It turns out that when you put the 2 grams of sodium hydroxide in here, the 2 grams of sodium hydroxide actually adds to the total mass. So think of it this way. You have a reaction vessel that has 100 milliliters, so 100 grams of your solution. But then when you put the 2 grams in there, that adds to it. So now you have 102 grams. So this right here is wrong. This should be 102. Which means this right here is wrong. Let's recalculate. So we got 102 times 4.18 times 6.5. So 2771. So these get flipped. I'm glad we made that mistake, so that way we can keep track of it. Good. There it is. So you have to consider, because you can't really ignore those 2 grams are going to essentially make a difference. Now, the specific heat of sodium hydroxide is not the same as that of water, but to an approximation, we can say just add that together and assume that it works, and this will work. So this is how much heat is released. Released from the burning or from the reaction of 2.00 grams of NaOH. That's what we're saying. This is how much heat got released when only 2 grams of sodium hydroxide are burned or reacted. Now, we're asked for the delta H. Delta H is usually given on a per mole basis. In fact, our reaction looks like this. Our reaction should be sodium hydroxide plus hydrochloric acid. So we'll have to remember that this is a double replacement reaction. The sodium and the hydrogen swap places. This is actually a double replacement neutralization reaction. You get yourself NaCl plus H2O. What we're going for is we're going for this delta H at the end here. We're going for, what is the delta H? Now the delta H has to be per mole of the sodium hydroxide. Why per mole? Because the equation is balanced to be 1 for 1 for 1 for 1. This is a really simple equation. So we have to get kilojoules out here per mole. Right now we have joules. We've solved joules from 2 grams of sodium hydroxide. So to get it to kilojoules per mole, what we'll have to do is actually convert the 2 grams of sodium hydroxide into moles, and then simply divide the kilojoules by the moles. So let's do exactly that. If I have 2 grams of sodium hydroxide, I can convert this into moles by going from grams to moles. Now sodium hydroxide, the molar mass of sodium hydroxide should be exactly 40. You're encouraged to memorize some molar masses of important compounds like sodium hydroxide. 2 divided by 40 give us 0.05. So I have myself 0.0500 to keep with sig figs moles of NaOH. Now the amount of joules I have is 2771, so that's 2.771 kilojoules. So I have myself 2.771 kilojoules. And if I divide the kilojoules by the moles by 0.0500, I'll actually get myself kilojoules per mole. I'll actually get this value up here, what we're looking for. I will get that value. So let's do exactly that. If I got 2.771 divided by 0.05, which is 55.42. Now sig figs wise, we've got 2 sig figs. So 55 kilojoules per mole. 55 kilojoules per mole. So this is the final answer. So notice it's the same thing as before. We did the MCAT, and then we scaled it up to a per mole by converting how much we reacted into moles. Now we based it off of sodium hydroxide because the other compound, the other chemical, HCl, was actually an excess, so we didn't really care about this. That's what we based it off of, sodium hydroxide, because in the equation that's the limiting reactant. So once we converted that to moles, we simply divided the heat by the moles to get our final answer. Alright, hopefully this makes sense. Let's do one more concept, and we'll actually do this concept in the, we'll do a short video 11 for this concept. That way to keep it short. Alright, so we'll see you in video 11.